Welcome back to example 3. This is the first of our most important examples for this topic because we're not only going to be finding maximum and minimum turning points on a curve, we're now going to be relating them to real life scenarios. This process is called optimization, where we're going to be finding the highest or lowest values for a particular circumstance. And these are what I would predict your HSC questions, if you get some on this topic, are going to look like. Okay, so for this example, we have the equation for the expense per year given to us. And it is in tens of thousands of dollars to run a certain business model. All right, now here is our equation for the expense. E is equal to x squared minus 6x plus 12. So it is a very simpler parabolic model. Now it tells us where x is the number in hundreds of items manufactured. All right, so E is the expense and x is the number of items that are being manufactured to produce this expense. All right, I'm just going to go back to the top here because these two little parts may seem slightly insignificant, but they're going to be really important for our answers. That expense in tens of thousands of dollars and the numbers of items manufactured in lots of 100. It's really important that we don't neglect that all the way through, because when we give our answers, we're going to have to change those answers to express them in either tens of thousands of dollars for expense or lots of 100 for items manufactured. Okay, let's break this actual problem down a bit more and see what we've got to do. Our key verbs. Right the way through, we have find. All right, the first one saying find the expense of running the business if no items are manufactured. Okay, so this is when we're going to have to substitute for x being 0. X being the number of items manufactured. Okay, for part B, it says find the number of items needed to minimise the expense. Minimise, that's the super important one. This is going to mean us thinking about finding a minimum turning point. All right, so again, we're going to have to address the first derivative and when that's equal to 0 to find that. Next one says find the minimum expense for running the business. So all this means is, like before, we want to find, when we found the y value of our minimum and maximum turning points, all we're going to do is go and substitute the answer from part B back into that original function. So that's the easy endpoint. Right? But please don't forget the tens of thousands and hundreds of dollars. All right, let's go and do some working out. Things haven't changed just because we're moving to optimization problems. The first thing I'm definitely going to do is draw out my little table or sequence of my expressions and the derivatives of those expressions, first and second. All right, so here we have a bit of important information, our original function and the first and second derivative of that original function. They're going to be super important to find those minimum and maximum expenses. Okay, so part A, this was an easy one. It says find the expense of running the business, so find the value of E when we have no items manufactured, so when the number of items equals 0. Okay, so for this, we're going to write out our original function, but we're going to substitute 0 wherever we see x. Okay, so it's a nice, easy one to do, 0, 2. So obviously we get an expense of 12. Now, is this our final answer? No, that's right. We've got to go and make that exchange where we said, okay, yes, the answer according to our function is 12, but that means our expense is 12 lots of 10,000, right? Because the expense was in lots of $10,000. All right, so we've got ourselves $120,000 for our expense. Part A, done. Okay, part B, it read, find the number of items needed to minimise the expense of the business. Okay, so I've written down that word straight away, minimise. We're talking about, in this case now, when that first derivative is equal to 0, and we're looking for that minimum turning point. Okay, so this one's using a bit of our calculus now. Okay, so if I write my first derivative down, I had 2x minus 6. Okay, so we've got to solve this for when x equals 0. Okay, and we clearly get down to x equals 3. Now, if we've got, all this means is we have a minimum turning point if we're to graph this function when x equals to 3, or according to this scenario, we're going to have when 3 items or 300 items being sold, something's going to give us an expense in this scenario. To make sure it's a minimum turning point though, I'm going to examine that second derivative. Now, this is a nice one for us because our second derivative equals 2, which is greater than 0. So that means it's a concave up. All right, so it means we definitely have ourselves a minimum at this point in time. Always good to check. So to finish off our answer, therefore, 3 lots of 100, we have 300 items manufactured to produce a minimum expense for this business. Okay, the final part of this question asked us to find the minimum expense of this business. Okay, so we've done a lot of the groundwork for this question already in part B. That's where all the work was done. We said that the minimum expense is going to occur when x equals 3, or 300 items were being made. So all we do now is go and substitute that x equals 3 back into the original function. And this gives us an answer of 3. So to answer the actual question, our expense, our minimum expense, is 3 lots of 10,000, otherwise known as $30,000.